toolbar. I've added a screenshot of the toolbar here. You'll see how questions will be displayed and how answers will appear. Note that I recorded this image on a Mac, so your interface may look slightly different, but the function and layout should be more or less the same. Your questions can be technical if you're experiencing problems with software, or content questions about what is being discussed. If you prefer, you may also email my coworker, Kayla Mallon, whose email address is mallonk@si.edu. That's MALLONK@si.edu. We really would like a high level of participant involvement in this webinar, so please do ask any and all questions as they come to you. Now it's my pleasure to introduce tonight's presenter, Dr. Maria Varelas. She is a professor of science education in the Department of Curriculum and Instruction and Honors College faculty at the University of Illinois at Chicago, with degrees in science and in education. She is also the director of the UIC Center for the Advancement of Teaching Learning Communities. Her research focuses on classroom-based learning and teaching of science in urban schools that educate predominantly students of color in economically challenged neighborhoods. This research has been supported by over $9 million grants from the National Science Foundation, other foundations, the state of Illinois, professional organizations, and the University of Illinois at Chicago, as she works with urban school teachers to reform science education aiming at equity and social justice, and to explore possibilities and challenges that emerge in such efforts. Dr. Varelas is widely published, including in top-tier journals, and since 1993 has been teaching in UIC's K-8 teacher education programs and doctoral programs, receiving several teaching awards, including UIC's highest honor for teaching, the Award for Excellence in Teaching. She has been elected member of the Board of Directors of the National Association for Research and Science Teaching, and associate editor of the Journal of Research and Science Teaching, co-editor of the Learning section of Science Education, and higher education editor of Spectrum, the official journal of the Illinois Science Teachers Association. Dr. Varelas has served as a consultant to the 2012 U.S. Framework for K-12 Science Education. So, without further ado, Maria, I am passing you the controls for the presentation.
Excellent. Thank you so much, Kyle, and thank you to the Smithsonian Science Education Center for offering me the opportunity to host a webinar in the Laser I3 series. And thanks to all of you who have joined us today after a busy day, as many or all our days are in classrooms and schools. I'm going to try to move to the next slide, which I successfully did. So I titled my presentation Literacy Tool Use as an integral feature of student sciencing, and turning science to a verb, sciencing, to encompass the many verbs that I would need otherwise to use, such as doing, thinking, communicating, learning, and identifying with science, to just name a few. Now, the ideas that I will share with you today come from working with many school-based and university-based colleagues over the years. And although I present them to you today, I'd like you to take notice of the many names that I have on a couple of slides, as they have all contributed to shaping these ideas in and out of the classrooms. So I'm trying to actually move through these slides, and I can't. Oh, there we are. So also, I would like to underscore that the examples that I will share with you come from Chicago public school classrooms, many in schools located in economically challenged neighborhoods, some, and I'm going to stop here for a second and try to move to another slide, which I don't seem to be able to do, Kyle. Let me just see here.
I'm not sure why that's happening, but if you like, you can just verbally cue me and I'll move through them instead.
Okay, that would be great. If you would like to do that, so I'd like to go to the next slide, Kyle. So back to what I was saying, these examples that I will share come from Chicago public school classrooms, many in schools located in economically challenged neighborhoods, some in the west and some on the south sides of the city, with many, or the majority really, of students qualifying for free or reduced lunches. So almost most of the students are Latino, Latina, or African Americans, mostly attending schools with other students who share their racial and ethno-linguistic heritage, as really Chicago is one of the most segregated cities in the US, as we know. So for me, this is really a critical point, as for over my almost 30 years, 30-year career, I have tried to understand, unearth, and celebrate what students from historically marginalized communities and who are often positioned as having all sorts of gaps do when offered opportunities in classrooms. So, Kyle, I don't think we're moving through the next couple of slides. Could you please do that? Great. So, perfect. So you will see here some names, and of course, they're going to be available on the web. Now, let me move to the next slide, Kyle. Thank you. So let me first start with you sharing with you what I consider to be important principles that guide how I teach science and how I work with both in-service and pre-service teachers, since the various literacy tools that I will discuss with you throughout the presentation serve to enact in classrooms these principles and need to be used, I believe, consistently with these principles. So science is about understanding the world around us, and such understanding develops from what I call a dance between observing, experimenting, and explaining. So now reading, writing, drawing, talking are all critical aspects of scientific activity, both at the data level when we conduct observations or do experiments, but also at the theory level. In other words, when we develop a network of ideas that explain how the natural world works. Now also, text and hands-on explorations can complement each other, allowing us access to both levels of scientific activity. Now, by texts, I mean multimodal texts, texts that are not only written, but also oral, and texts that do not only include language, but also other modes of communication, such as visual images, for example, drawings, diagrams, photographs, but also bodily movements or performances, concept maps, tables, graphs, etc. So moving to the next slide, reading multimodal texts as well as producing multimodal texts are necessary for both developing and communicating scientific ideas and practices, because we know that thought and language, or more generally communication, are intertwined processes. So as we use multimodal literacy tools and hands-on explorations to teach science, we need to strike a balance, I believe, between creating spaces for students to offer, test, develop their own ideas in the midst of the classroom community, and also guiding them towards more articulated understandings. And this balance is the essence of what I call dialogic teaching. Now, such dialogic teaching supports, I believe, the building of connections. That is an important part of meaning making. So in the process of meaning making, students develop and express emerging ideas and language that may not be scientifically correct, but that I believe nevertheless should not be suppressed or avoided, but rather celebrated and built upon. So now let me turn to the first important tool, read alouds of information books. Can we go to the next slide, please? Kyle, good. So, and also at this point, let me first do a poll to see how many of you are using information books in your science teaching. So on your screen, you will see the poll that Kyle put up for us. So can you please take a few seconds to select whether how often you use information books in your science teaching, never, sparsely, or frequently. Maybe we'll wait a couple of more seconds and we can stop in about 10 seconds the poll, Kyle, and then see the results.
Sure. Almost everyone is.
Great, wonderful. So now let's, so we have about half of you using it sparsely and some of you using it frequently. Let me now also, Kyle, if we can, do another poll before we move to the conversation about information books, and ask you to select whether it's never, sparsely, or frequently that you read aloud such books to your students, as opposed to only letting them read the books individually or in small groups. And we'll wait a few seconds for you to lock your choice. Excellent. So we have really half of you, or a little bit less than half, sparsely or frequently reading aloud such books, and a few of you selecting never. So let me go back to the slides, Kyle, and go to the next one, please. Excellent. So now science information books are available on many science topics, as we know, and some are trade books, also called picture concept books, composed by children's authors and illustrators, and others are composed by curriculum writing teams, such as the writing teams for the STC, the Science and Technology Concepts program, that many of you are familiar with and use. Which is part of the STC literacy series, for which I was actually a scientific and educational contributor to the K2 books. One of them that you see on the screen here changes. Next slide, please. So now, information texts have a lot of benefits. They discuss scientific ideas in the context of everyday activities and phenomena. They help students encounter scientific, academic language, actually, scientific academic language, and learn the language of science beyond just vocabulary words as they engage with linguistic registers and genres that characterize science as a discipline. And they have also relatively more abstraction, generalization, typicality, and accuracy, among other features. And also, as expository information texts, they include structures that are compatible to the cross-cutting concepts and scientific practices that the framework now emphasizes, such as cause and effect, compare and contrast, description, sequencing, and many others. But what is most important, I think, is how we use such texts in the classroom. As we know, textual engagement is an interaction between the text and the reader or listener. So read alouds of multimodal texts offer students opportunities to bridge their own knowledge with the scientifically accepted understandings that are presented in the books, and thus, I believe, create more sophisticated ideas. Next slide. So the key, though, is that the sharing of the text is dialogic. So what do I mean by dialogic sharing? Well, we do not wait till the end of the read aloud to invite students, often by posing questions, to share their thinking about the ideas presented in the book. But instead, we create as teachers opportunities for students to reveal and communicate their interpretation, inference, and comprehension throughout by asking questions, just flipping through to a page and waiting for the students' reactions, by inviting the students to look at the images and share ideas that come to mind, or modeling our own thinking about ideas presented in the book. Now, sometimes we find that what we consider details as teachers may offer some students actually opportunities to participate, make some meaning, and engage with science. Next slide. So what we have found in our research is that as teachers and students engage in dialogic read-alouds of science informational texts, they employ a very beneficial strategy called intertextuality. Now, intertextuality is the act of referencing other texts, the juxtaposition of other texts to any current texts that have been currently considered, read, discussed in class. So now, if we take an expansive view of what counts as text, we can consider written texts, texts that are orally shared, such as songs, other media, such as TV shows, prior classroom discourse, recountings of hands-on explorations, or recountings of experiences or events outside of the classroom, all as potential texts that can be juxtaposed with the texts currently read, so that connections can be made. Now, having studied classrooms, what we have found is that although at the beginning of the year, teachers are the ones who initiate more of the intertextual links, later, students do so. And it's worth noting that boys and girls seem to contribute equally to intertextuality. Also, as a science unit progresses, there's a shift from connecting the read-aloud text with recountings of personal experiences to connecting it with other written texts, prior classroom discourse, and recountings of hands-on explorations, which for me is an indication that the connections between scientific ideas and the students' everyday reference have been established, and the class is moving towards strengthening the connections among scientific ideas themselves. Next slide, please. So let us look at an example of the role and the functions of intertextuality during read-alouds. So here's an excerpt from Begonia's class. So Begonia, the teacher, shown as T in the classroom discourse excerpt. Begonia was reading the book When a Storm Comes Up to her students. Now, she has read what's in the caps on your screen. So she has read: a tornado forms over land, the winds whirl around in a tall funnel-shaped column, cars, roofs, even entire houses can be sucked up off the ground by a tornado. The government, and she stops there and says, okay, we got to the tornado part of the book. Okay, and she sees really Caitlin raising her hand, so she says, okay, tell them. Speak to the class, tell them what you want to say. So Caitlin says, tornadoes can hop and twist around, or wiggly-waggly, or just around and around and around in a great circle. And I have a book of tornadoes that has this picture where there's a damage to one house right here and a house that hasn't even been touched on the other side. And it's bold because this is actually an intertextual link to another text, that another book that Caitlin has read. So Begonia says, well, a tornado could go down on the same street, and you could have one side totally damaged and the other side fine, paraphrasing what Caitlin said. And then goes ahead and says, well, I'm going to pick Danielle and Natasha because they hadn't had a turn yet, and Anna, all right? So Danielle is taking the floor. So says, what do you mean by tornadoes can hop? He's asking Caitlin. So Caitlin said, well, in the book called Tornado Turbo, I read The Magic School Bus, and Begonia is trying now to clarify, is it one of the books we have here? Yeah. Next slide, please. So, and what Begonia does is she wants kind of frame for the students that we have these books in the classroom. So we do have Twister on Tuesday, she says, and The Magic School Bus. Wait, back to her. So she's giving the floor back to Caitlin. Well, Caitlin is answering the question and says, well, it can hop. It can go up for a little while, then go down, go back down, and skip a house very easily. So she's describing what hopping, tornado hopping is about. So okay, so guys, Begonia says, think of it this way. If you are walking down the street and you guys are playing a game or something, there's a twig or a tree, how many of you guys, oh, you know what my son does? He loves hopping on the tiles, you know. If there is red and black tiles, he will hop on all the black ones. That is kind of what a tornado can do, which here, Begonia makes an intertextual link to a recounting of kind of an everyday experience, an event outside the classroom, outside the school, and turns to Natasha after validating kind of Daniel's question, saying, good question, Daniel. And Natasha saying, in a book I have at home, talk to them. She's asking her to look at the rest of the classroom. It says, sometimes by Florida, a lot of tornadoes come out of the water, and they are called water spouts. So here, Natasha is also making another intertextual link to another text, but also is, through that link, is introducing a new scientific term, water spouts, that can be used later on to think more about tornadoes. So Dialogic read-alouds of information text offer students opportunities to develop and share ideas, but also to engage in a much desired act in science, reasoning. Next slide, please. So in another example, in Nevin's classroom, she was reading a chapter of one of the book. The book was called Earthworms, and the chapter specifically was tunneling. And after reading what's again on in caps, this worm is slipping through a hot, dry summer in a burrow deep underground. One of her students, Kira, offered what you see also in your screen. So Kira said, worms, they can't stay in the sun because they might get too dry. And after a few seconds, Kira interrupted Nevin, who started reading, continued to read the text, and added a small story to what she had just shared earlier. So Kira said, one time my friend, he got a worm from the dirt, and then he left it on the bench, and I was watching it, and then I went to go play, and then when I came back, and it was all dry, but it died. So the way I'm making sense of this is that although the book referred to a worm being underground, Kira focused on what would happen above the ground, and established a cause and effect relationship between exposure to the sun and drying out. So in this way, Kira justified that what she had heard and seen in the book by considering an alternative situation and by sharing a mini story recounting an experience she had. So in this way, she linked together a series of ideas, which are like worm movement from underground to the surface, exposure to the sun, drying out, and dying. And which is, for me, what scientific reasoning is all about. As a matter of fact, this last example comes from a study that my group and I published recently, where we analyzed how science texts and hands-on explorations facilitate meaning making. So as you see in this slide, what we found is a synergistic relationship between informational texts and hands-on explorations, which means that they are both significant and useful because they offer different access points and pathways via which students and teachers co-construct understandings. So for example, in the earthworm lessons, read-alouds offered opportunities for various types of reasoning and making sense of ideas that the students have encountered in the hands-on explorations, whereas the hands-on explorations with real worms offered them opportunities to expand and nuance some of these understandings of earthworm features and behaviors, noticing some more specific things about the worms, exhibit sensitivity to suffering, for the worms, and consider ethical treatment of animals, how you handle the worms, something that didn't emerge really during the read alouds. So next slide, please, Kyle. So let me now switch to another element of multimodal communication and literacy that is useful to science teaching and learning. And let's first do a quick poll again to see how many of you are using dramatizing or acting out in your science teaching. So can you please take a few seconds and let us know whether never, sparsely, or frequently you're using dramatizing or acting out. Okay, so it's kind of split between some of you using it sparsely and half of you about never, and only a small percent using it frequently. So let's think a little bit about what dramatizing and acting out can offer us in science classrooms. So what does drama have to do with science learning? Well, classroom drama activities are, I believe, kind of a unique tool, a semiotic tool. And by semiotic, we mean a tool related to signs and representations, where meanings are expressed and developed simultaneously in visual, spatial, kinesthetic, and linguistic modes of communication. So in spite of successful use in language arts, reading and social studies, and the literature is telling us that drama has not been widely used in science teaching and learning. Now, dramatizing in general helps fill in the gaps in meaning. So think about it. In theater, both actors and audience use their experiences to mediate and understand the performance. And the performance helps them mediate and understand their experiences in the world. So what children learn, what students learn in a dramatic enactment in a classroom helps them extend their understandings. Now, during drama, people create imaginary worlds, right? So that allow them to think and to link their own experiences with the unknown or outer social or physical world. Now, as these links are established, actors and audience move back and forth between the actual world and the imaginary world. So what is also important is that in dramatizing, emotion, feelings, affect are all integrally intertwined with more cognitive and social aspects like reasoning and thinking and interacting with others. Now, let me offer a couple of examples of using drama in science classroom and show you what happens when students immerse themselves in science phenomena and become the things that they were learning about. So now, such drama activities are what is called process drama. Now, that allows learners to use imagined roles to explore issues, events, ideas, relationships without an a priori detailed script. So we'll go to the next slide. Now, one dramatic enactment can be acting out the micro configuration of molecules associated with the macro states of matter, solids, liquids, and gases that we experience in the natural world. Now, students can become molecules of a substance, and they can perform what molecules do in different states and when changes of states happen. Now, students figure out how to position and move their bodies in relation to each other in a configuration marked on the floor with masking tape, as you see in the pictures, and depicting an ice cube sitting at the bottom of a cup. Now, in the left picture, on the screen, as a solid ice cube, they try to represent that they are close to each other, they move a tiny bit, and that they are tightly bonded with each other. Now, as they melt and become liquid water in the middle picture on your screen, they show how their hold really gets loosened up. They spread to the edges of the cup, and they move much more. Now, as they vaporize, in the right picture on your screen, they represent how they are separated, move fast, and are not anymore bounded by the walls of the cup. So then, as they hit cold surfaces, they condense, turning to liquid representations that they have to reenact and get to what it looks like in the middle picture. And as they put in the freezer, they find ways to turn back to their solid representation, so the cycle can start again. Now, as the students engage in the molecule drama, they begin to make differentiations between the micro and the macro world. So, for example, in one classroom, whereas some kind of earlier groups, as they were enacting being molecules, were melting by falling down, like the way that ice cubes melt at the macro level, the picture as shown in the picture on your screen, right, under the middle picture. Now, later groups started to melt by loosening their hand and arm bonding, spreading and moving faster. In that way, really representing the micro way, really thinking that they are molecules. Now, in another classroom, the teacher, Jennifer, actually, asked her students, we're going to start to do what? As she pretended to crank up the heat underneath the cup. And the students offered both melt and get looser. So in this way, they were relating the macroscopic process, melting, with a microscopic process, molecular bonding, becoming looser when solids turn to liquids. And they also connected the scientific term of the process, melting, with the actor's action of getting looser. So, and yet in another class, in Ibet's bilingual Spanish-English class, serendipity played an important role in helping students connect what they were doing with the scientific ideas. When Ibet's student became vapor, as you see really on the right picture on your screen, they started running around and bumping into each other. As soon as Ibet noticed that some of them bumped into each other, she said, oh, look over there. They bumped into each other. That's what happens. The molecules bump into each other. In that way, helping her class develop a model of the micro world of matter, which came to her mind as she saw her students enacting the movement of molecules in the gaseous state. Next slide, please. Now, another dramatic enactment of a life science unit can be acting out interactions among entities, living and non-living, in an ecosystem, representing a food web. Now, students can take the roles of animals, plants, and non-living entities that are indicated with name tags that you see the students really wearing, and negotiate a place in the web of the various entities connected by strings. You see the strings in the pictures too, red strings in the case of these classrooms, as they think who eats who. Now, as students engage in the food web drama, they discuss animal characteristics vis-a-vis the place of an entity in a food web, and they consider what I call, I guess, the relative importance of some entities in the forest ecosystem. So, for example, in one classroom, children realized that plants were fundamentally in a food web because they noticed that the girl who represented a plant was needed for their food web to work. Now, in another classroom, students realized that when an entity disappears from the ecosystem, others would be affected as the strings that they were holding dropped to the ground. But they also realized that they have to consider what else may be providing food for that animal before they conclude about what would happen to that animal. Next slide, please. So what's also interesting is that during these dramatic enactments, the students' bodies operate on multiple levels. As material objects, they move through the space. As social objects, they negotiate classroom relationships and rules. And as metaphorical objects, they stand for, say, molecules in the various states of matter or for entities in a food web. Now, for example, in one classroom, the teacher noticed that her students enacted freezing by stopping any movement rather than moving just a tiny bit. So the students in Anne's class knew that when she asked them to freeze, she really wanted them to stop doing what they were doing. So Anne had to have a discussion with her students about the difference between the freezing directive as part of their classroom routines in the real world of the students, their classroom, and the freezing of molecules that the children were enacting in the imaginary world of the science phenomenon. Now, in another classroom, children's gendered lives were intertwined with they're pretending to be molecules in a state of matter. So boys and girls actually giggled when they had to be with someone of the opposite gender, holding hands or being too close when they were representing a solid. And at that moment, the teacher, Naveen, really reminded them, do we care that he's a boy or he's a girl? No, we are molecules. Do it for science. And actually, this is, in fact, has become a legendary saying among our team. Now, in another class, a student had to negotiate being at the end of the line of a group in of a group in class, and being at the low level of the food chain because other entities feed on it. Now, as a termite, and as the chain was taking shape, a boy actually announced that, damn, this sucks. I'm going to be all the way at the end, which is not usually a flattering position, right, to be in a school line. But this gave the class an opportunity to discuss the boy's, who was actually representing a termite at that point, significance and importance in the ecosystem. Now, so such dramatic enactments of scientific ideas enable students to do a kind of what I call imagining in science that may not do otherwise. The imagining requires playing around with what representations would look like, what they would mean, and why. So when the students take roles such as actors and directors and viewers, audience, it allows them to engage with science content from multiple perspectives. And let me emphasize here that many of our students see science as, we know, rational and cold and unexciting and lacking any emotional content. So in some ways, drama is totally different. And therefore, dramatic enactments contribute to infusing science with emotions, excitement, fun, interaction, and shorten the distance between the object of the study and the subject. And in this way, I think they provide a more holistic experience to learning science. So orally sharing and discussing illustrated text with students and engaging them in acting out science phenomena are two important, I believe, tools that we know can enhance student thinking, reasoning, explaining, making connections, and thus learning and identifying with science. Now, both of these tools that I discussed so far are more collective productions among several students and, of course, the teacher. Next slide, please. So now let me turn to another tool that is individually produced, but of course shaped by collective understandings. And this tool is composing an illustrated science informational book related to the science unit that the class has been studying. So the poll is on your screens now, so can you please take a moment and indicate how often you get your students to create a book on a topic of their choice as part of their science class. Great. So, well, almost half of you have never done that, and some of you use it very frequently, and others sparsely. So let's think together now, and we'll go to the slides back again, Kyle. And as we see, right, creating multimodal books. Now, so let's think about ways in which students can create multimodal texts in their science classes and examine the benefits that such creations have for instructional and assessment purposes. Now, we know that it is important for students to be offered opportunities to communicate science understandings. And actually, in previous webinars of the Laser I3 series, several of them have been discussed. Now, two internationally known educators and researchers of multimodal communication, Gunther Kress and Theo van Leeuwen, have argued what you see on the screen as a quote from their paper. Representation requires that sign makers choose forms for the expression of what they have in mind, forms which they see as most apt and plausible in the given context. And they also argue that visual representation is as important as language, as kind of the two bring out two sets of meaning that are neither, as they say, fully conflated nor entirely opposed. So visual images, pictures, drawings, diagrams that students should be given opportunities to create can offer us, the teachers, multiple related windows into their minds. Next slide, please. Now, one way we can incorporate bookmaking into our science class is by asking students to individually compose books at the end of a unit. Now, in the work my team and I have been doing, students were given some directions that you see on your screen. So students were told, write about a part of what we have studied in the unit, something that other students who haven't studied this unit would like to read. Also, they were told that your book should include both writing and drawing to remind them to make multimodal books. Your book should be like the books we have read that have print and pictures, because in these classrooms, students have been using a lot illustrated information texts. You can look at our semantic map, your journals, and other things we created during the unit that may have been displayed around the classroom. But this book should be your own book on a topic that you are interested in, not something that you have copied from other books. And you won't be able to write and draw about everything we studied, so you will decide what to include. And in making your book, you should think about what ideas you want to explain in writing and what ideas you should explain in pictures. Next slide, please. So when students are offered opportunities to choose a topic to write and illustrate, they actually produce, we found through our own research, magnificent products filled with wonderful ideas, expressions, coherence, and individuality. And they prove, we believe, what Kress and van Leeuwen claimed, another quote that you see on your screen, that their drawings are not just illustrations of a verbal text, not just creative embellishment. They are part of a multimodally conceived text, a semiotic interplay in which each mode, the verbal and the visual, is given a defined and equal role to play. So this means that when we assess student science knowledge that they communicate through their books, we need to pay attention not only to their words, but also to their images. So let's look at a few examples. Next slide, please. So here's a page from Vittoria's book. When I look at the page of the book that the student has composed, I try to identify the ideas that the student has communicated in either words or pictures or both. So on this page, Vittoria communicated several correct ideas about solids, liquids, and gases, and their characteristics and how they change. So Vittoria shows that she knows that solids, like the snow and the ice on the bottom left, have their own shape, but liquids, as shown in the container to the left, do not. So liquids spread at the bottom of the container. These are ideas that Vittoria only showed in her drawings and not in her written text. Now, the idea that melting requires heat is communicated in both modes. Vittoria wrote that it melts in the sun and in the hot air and drew a yellow sun. However, what changes of matter are involved in melting is presented by a combination of words, such as ice, snow, melting, and images showing liquid water spreading out and solid water in a certain formation. So yet another idea that water evaporates from the open container, which she writes, keep the lid off, and forms clouds, is actually only shown in her picture with these blue vertical arrows pointing upwards to a black cloud. Now, it's also important to keep in mind that making time in our classrooms so that students share orally their books, either with the whole class or in small groups, or even only with the teacher, is an essential part of learning. Now, in presenting her book, Vittoria said about the vertical arrows point to the black blob, that water vapor is going to the clouds. So in that way, she made explicit the meaning that she wanted to represent in these blue arrows. Next slide. So now, looking at another example, here's Stephanie's page, a page from Stephanie's book, where she presented her idea of frog reproduction. She expressed several ideas in words, that the mother frog lays eggs, it takes a long time, and it can lay up to 4,000 eggs. But others in her picture, other ideas she expressed in her picture, like she has drawn small circles with black dots in them, and for which, when she was presenting it orally, she said, this is the egg, and the white circle around it is jelly to protect it. Now, what we have also found is that students, even younger ones, find sophisticated and intriguing ways to represent their science understandings when given the opportunity. The next page, where we're going to see really an example from Pablo's book, is a wonderful example of that. Now, Pablo communicated two properties of gases on his page, that they don't have their own shape and they are invisible. Now, although not all gases are invisible, the teacher knew that Pablo was talking about water vapor. So on the top third of his page, we see that Pablo communicated the lack of a specific shape, both in words and by drawing what he called water molecules, these blue dots, across the page, a bounded space by the line he had drawn. Now, the blue color of the molecules, of course, is not scientifically correct, but given that he had thought water was blue, again, a scientific misconception, he made sense. It made sense to him that he colored the molecules blue. Now, in the middle section, Pablo referred to both properties. Gases disperse all around and you can't see it. Now, interestingly, he again depicted dots for molecules, but now his dots were smaller, but still blue. And he orally shared that he had made them smaller than the ones on top because he wanted to show that he cannot see them, although they were the same molecules. Now, the most interesting part comes here. In the bottom section, he reinforced the idea that gases are invisible, both in words and in his picture. Now, you may be wondering, what picture am I talking about? Because it's mostly blank, really, under his last sentence. Well, if you look more closely, you could notice very faint black tiny spots. So Pablo explained, as he presented, that he used his pencil with a black lead, which was well sharpened, instead of his blue crayon, to make as tiny dots as he could, because gases are invisible, and he didn't know how else to show, really, visibly, something that's invisible. So I believe that Pablo's really page shows us in beautiful ways how he had developed meaningful scientific ideas that he truly owned. Next slide, please. So let me wrap up, because we're coming close to the end of our time. Let me wrap up this part by highlighting some of the findings from studies we have done on illustrated books that students have composed as culminating activities of science units. Now, since students have a choice in what and in how to write and draw, most of them produce coherent and rich books organized around a theme that they reflect in the title of their books. Now, we also found that their voices and their ideas come through their books, but also what gets represented is more collective understandings that they developed with others in the class. Now, overall, they include accurate scientific content and use a variety of ways to represent and relate their ideas in both text and pictures. They also show audience awareness, which is an important idea, because they decide to include in their pages and structure them in such a way that they would teach, as they say, others particular science ideas that they know themselves. Now, in this way, I claim that they position themselves as knowers of science, and they seem to be writing with a purpose. The purpose to share their science ideas with others, an authentic purpose, as opposed to only showing the teacher what they know. Next slide, please. So in conclusion, literacy tools are indispensable for teaching and learning science. There are several such tools, but today I focused on 3 of them: read alouds of informational texts, dramatic enactment of science ideas, and authoring illustrated science texts. Now, these tools offer students ways to both extend and develop their science understandings and share them with others, so that others and themselves examine them and learn. So students make sense through the use of these tools, as at the same time they exhibit their knowledge and competence in science. They are also, we have to remember, these are also tools that scientists use in their practice. And although the engagement with informational text and the production of multimodal text seem pretty much commonsensical, you may be thinking about that it's far-fetched to think that scientists dramatize science ideas. Well, after all, we don't see them, scientists acting out how molecules move, or how igneous rocks are formed, or how animals and plants connect in the food web. However, Beth Warren and her colleagues at Turk remind us that scientists, both in life sciences and physical sciences, do a kind of imagining that's involved in dramatizing to explore how a phenomenon unfolds and how a process happens. So take, for example, Barbara McClintock's work and her revolutionary idea in genetics. Now, McClintock had to have what Evelyn Fox Keller called a feeling for the organism. She had to become part of the organism, the corn that she was studying, in order to imagine this idea of jumping genes that she called, and how they are transported within the DNA to affect the color of the grains. So I claim that engaging students in dramatizing, as well as reading and producing multimodal texts, offer them opportunities to not only learn science, but to engage in practices which the practitioners of that domain themselves use to produce new knowledge. So I'll stop here so that we have time for questions, but let me first point out the last 2 slides. So Kyle, if you go to the last 2 slides, please. Here I included bibliographic information of the references I made in previous slides, but also I'm providing you in this slide and the next some relevant publications of my team that my team has published in case they are useful to you. So thank you, and we can take some questions now.
Thank you very much. And just a reminder to everyone, you don't need to scramble to write down all of these references. The PDFs will be available after the fact. We had some feedback when I was unmuted earlier, so I'm going to test that just for a quick second. Does this audio sound okay, Maria?
Yes, that sounds fine. Thank you, Kyle.
Great. So we do have a few minutes for questions and answers. If you're able to, please enter any questions into the GoToWebinar toolbar, and we can go ahead and get a few questions answered. So one question that came up, the person asks if there's a way to integrate formative assessment with some of these tools, and it's sort of taking them to the next level, perhaps.
That's beautiful. That's a wonderful question. You know, in my mind, formative assessment is intertwined with instruction that we do. So as the students, for example, dramatize and enact ideas, we notice what scientific ideas are kind of crystallized for them and what they're still struggling with. So we can take what we see as feedback from them and then try to work with them either in groups or as a whole class, revisiting some of these ideas and actually asking them to make any adjustments they think in their enactment, in their dramatizing, to actually show now their more developed ideas that we help them strengthen after the conversation that we had or after another day in the unit. Similarly, I think your question can help us think about how we can have, for example, books developed as the unit unfolds. And then the students can go back and revisit some of the pages of their books and revisit their drawings, their illustrations, or revisit their text as they learn more throughout the unit. So these tools, these literacy tools, are, I think, extremely versatile for us teachers of science, that we can be using them as instructional tools and formative and summative assessments, depending on the variety of tools that we would like to use in that particular unit.
Great, thank you. So it looks like we haven't had any other questions come in. As a plug, I would add that if the audience is interested in learning a little bit more on a related subject, we had a previous webinar on student notebooking specifically in science learning and teaching. So I'd encourage people to check that one out on our website. And Dr. Varelas, I want to thank you very much for that wonderful presentation and sharing your passion and expertise with us. Thank you very much.
Thank you very much, Kyle, and thank you to all the attendees. I appreciated the opportunity to share these ideas that my team and I have been working on for years.
Thanks again. And again, this webinar has been recorded, and the recording along with a PDF copy of the slides will be made available on our website within a few days. Finally, when you exit this webinar, you will be directed to a very short survey. We greatly appreciate your feedback, and you're taking a small amount of time to respond to those couple questions. If for some reason it does not pop up in your browser when you exit the webinar, it will also be included in the follow-up email sent by GoToWebinar tomorrow evening. You're also very welcome to email us with any additional feedback. So again, thank you for attending, and have a great evening.